Hi guys, so this is our intro to polar coordinate system and polar graphing. This is more aligned with 6.5 than it is with 6.4, but I just wanted to get you an idea of what you were in for the next couple sections. This is normally one of my favorite lessons to do for this chapter. We do it as a in-class together exploration where you would graph these on your calculator and then draw some conclusions about the graphs and how to get from the equation to the graph, how the equation and the graph are related. And then we would test those conclusions with the last row, the fourth row of the exploration. So we're going to kind of do the same thing here today. So what I'd like you to do is get out your graphing calculator, or if you don't have it, you can go to like the Desmos grapher, and you can type all these into the Desmos as well. But just for next year and the year after, you may as well go ahead and get the practice of doing this on your graphing calculator is what I would recommend. So please change all of your settings to the settings that I have marked here. You would go to mode, and where it says func pair pole seek, you change the mode to the polar mode. You'd also make sure that you're on radians. Doesn't actually matter, I just want to be consistent with everybody, so we're going to make that radian mode. That's what you're going to see most of the time anyways. And then hit the window button. Even though we don't have anything in the graph yet, that's fine. I'd rather get the window all shored up first. So I'd like you to change your x min and x max to -5 and 5, your y min and y max to -5 and 5. And then where it says theta min, go ahead and let that be 0, and theta max, let that be 2 pi. And theta step, I believe the default is 0.13 or something, that's fine. Or if it's not, go ahead and change it and make it 0.1, and then you should be good to go on that. After we've adjusted that window, we're going to change it a little bit. We want to square it up so that we see even increments for the x unit and for the y unit. So then after you hit the window button and do all that stuff, then hit zoom and find the one that says zoom square and pick that. And then once you've done that, you are totally ready. So go to the y equals button, and I'd like you just one at a time. Don't put all these in on top of each other, or you're going to have a hard time figuring out which is which. So one at a time, and then change them, or put them all in, and then but turn off some of them by hitting the equals button, moving your cursor and just toggling those graphs off if you'd like. It's your choice. I would just put them all in y1 and then change it and make a new y1. So I would like you to graph these and sketch what you get on each of the four. Put each one on a different polar graph grid. Do the best you can. I know we haven't talked about polar graph grids. It doesn't have to be perfect, but try and get the major features there. And pause the video while you do this, and then we'll start, and you can see if you graphed them right, and then we're going to make some observations. So pause. And then we're going to start in 3, 2, 1. Okay, so now you have them all graphed, and hopefully they look like this. This is what the graphs of those equations should look like. So then I'd like you to make some observations. So types of observations that you could make are what would be if these look like flowers maybe, I've heard that in the past, what would be the length of the petal of the flower? How many petals does each one have, and how is that related to the equation? How is the length related to the equation? Also, is there a consistency in where the petals are oriented? You may be able to tell that, you may be not. So think about those things, pause, and then in 3, 2, 1, let's see if you and I have some of the same conclusions. So first off, to me, this one looks like a circle. And guess what? It is. And then these 3 are actually all called roses. So if you thought that they look like a flower, good job, because they are called roses. Let's see, what else? If we're looking at the petal length, it seems like the petal length is 3 in each of these cases. And I can see that because here this is 1, 2, 3, 1, 2, 3. You have tick marks every unit on your graphing calculator. So that's how you could tell that the petal length is 3. And my guess is that maybe that aligns with the 3 that would be right there in front. Just a guess, an educated guess maybe. If we're looking at the number of petals, so the first one where it was 1 theta had 1 petal, but it's a circle, right? And then when it was 2 theta, it had 4 petals, so not the same. When it was 3 theta, it has 3 petals. When it's 4 theta, it has 8 petals. So do you have any observations that you could make or any conclusions that you could hypothesize? Turns out, if we go ahead and give this a template form and we call this type of equation r equals a times the cosine of n theta, there you go, then we can start talking about, and you might want to write that on your worksheet as well, then we can just start talking about as far as the number of petals. When n is odd, then there seem to be n petals. But when n is even, there seem to be 2n petals, right? Twice as many petals if that number was even. So there you go. Hopefully you came to some conclusion similar to that. And as far as where the petals are oriented, this one is on the positive x-axis. Here there's one on the positive x-axis, and then here and here there's also one on the positive x-axis. So we can say that the first quote-unquote petal is on the positive side of the x-axis. And that's pretty much all the conclusions that we're going to make for this set. Okay, so use that now, and I'd like you to predict, if you can, just in your head, don't write it out, but predict if you can what these are going to look like, and then go ahead and graph them in your calculator. Keep all the settings the same as what you had before. Pause the video, and then we're gonna chit chat in 3, 2, 1. Hopefully here's what you have for your graph. So let's take a look at these and see, do our observations from before match our observations here or not, or are we learning something new? So since it's r equals 4 sine theta, that is consistent with our previous observation that if I'm looking at r equals a times the sine of n theta, that, there you go, that whatever a is seems to be the petal length. Because here this goes up to 4. Here is hard to tell on your graphing calculator, but you can tell on my graph that it goes out to 4. And then here you can tell that this bottom one that's on the negative side of the y-axis goes to 4. So I would think it was a safe assumption that we can say that A is the petal length there. Did our observation with the number of petals holds true here? And yes, it does. So good job if you made that observation again, that if n is odd, then there are n petals, but if n is even, then there are 2n petals. The only thing that might be different than what we expected, I would think is different than what you expected. If the cosine one always had one on the positive x-axis, my thought would be that the sine one would have 1 petal on the positive y-axis. And you'll see that that is not true. The first one does, but the other ones don't. So if you actually go back and you watch your calculator graph them to see where the first petal is, see if you can go back, watch your calculator, like retype it in so that your calculator has to graph them again, and then watch where the first petal is so that you know which one is the first petal, and see if you can figure out the pattern, like where, how you could figure that out from the equation, that fact that it's a sine. So pause the video and we'll chit chat in 3, 2, 1. So I don't know if you could figure this out or not. This is one of the trickier ones, so if you did, make sure to give yourself a pat on the back. So it turns out when n is 1, we won't say n, we'll say petals. So it turns out if there is 1 petal, then that petal is at 90 degrees. And yeah, we use radians more than degrees, but I'm going to talk to you in degrees for just a second because I think that it'll make it easier for you. So for the next one, when there are, okay, I take it back, sorry. I don't want to redo this entire video. So this is what you get. This is the live version. When n equals 1, the petal, quote unquote, is at 90 degrees. But when n equals 2, which is the second case, so there are 4 petals, right? N and the number of petals are not quite the same. But when n is 2, notice that the first petal appears at exactly what looks like halfway in between the x and y axis. So the petal would be at 45 degrees for the first petal. And for n equals 3, the petal looks like it's at 30 degrees. And for n equals 4, the first petal, if you watch it graph, looks like it's less than 30 degrees, you can tell. So it turns out it's actually at 22.5 degrees. And so what's the pattern there? Well, I'm so glad you asked what the pattern is there. Turns out that in each of these, that's 90 divided by the number of petals. And I hope that you could maybe figure that out. I don't know. So the first petal is going to be at 90 divided by n. Sorry, not the number of petals. 90 divided by n is the location of the first petal, which is kind of cool. Also, if we want to talk about how far the petals are spaced apart, which you could have seen this from the last one, I guess I just took this as an assumption, that the petals are all evenly spaced apart, right? So if there are whatever the number of petals is, take 360 degrees and divide it by the number of petals, and that's the distance from one petal to the next, the angle from one petal to the next. So 360 divided by the number of petals gives you the angle in between the petals. So I hope that makes sense. Okay, and then moving right along. So now this is a different type of thing because now we have 2 terms here. So do the same thing. You are going to have to change your y max here to 6, maybe 7, and then go back and hit zoom square again, just to make sure that you get as high as you need to for this set. And then I go ahead and graph all 4 of them in your calculator, pause the flip chart, and then in 3, 2, 1, here you go. Here's what they should have all looked like if you did this correctly. So let's again make some observations. So notice that all of these are on the positive y-axis in this case, and that might have to do with the fact that this is a sine function, so we could see, like, we could conjecture what we think it would be if it was a cosine. We also can look at how tall each one is on the y-axis and how low it gets on the negative side of the y-axis, and then how far over it gets on the x-axis. Those are the patterns that we're going to look for. So if you want to make some conjectures, go ahead and pause the video, think about that, look at where it hits the y-axis and where it hits the x-axis. 3, 2, 1. Okay. So I hope that you're exploring and you're not just waiting on me to tell you, but here you go. We're going to go ahead and call this y equals a plus b sine theta. And so we can talk about it using a and b all together. So turns out that the positive y-axis is where the majority of it falls, or where the maximum is going to fall, in this case, right? And we get that the maximum, look at the first one, it went up 6 units, but then the second one went up 5 units, and then the next one went up to 4, and then the next one went up to 3. And if you look at the equations, 6, 5, 4, and 3 are what you get if you would take A plus B. Now let's look at the minimum. So the minimum here on the first one, it looks like it's a radius of 2, right? Now it's a y coordinate of -2, but we don't care about that. We care what the radius is. So the radius there is 2. The next one has a minimum here radius of 1. The next one has a minimum radius of 0. 2, 1, 0. What is this? Did you figure it out? This is actually a radius of -1, which is why it like goes up in on itself. And so it turns out that the minimum is going to be A minus B, because that's what you're going to get. 4 minus 2, 3 minus 2, 2 minus 2, and then 1 minus 2. Turns out that this is, you're always going to achieve the maximum when sine theta equals 1, which is the maximum that sine theta achieves. So you might be able to figure that out. And it's going to achieve minimums when sine theta would be at -1. So that's a good way for you to find those maximums and minimums. And then let's look at the sides. So this is just parenthesis material. Okay, and then let's look at the sides. So the sides, in the first one, the side is 1, 2, 3, 4. In the second one, the side is 1, 2, 3, and both sides, right? They're the same. In the second one, it's 2, and then in the last one, or third one, it's 2, and then in the last one, it's 1, which means that the side radii are just whatever A happens to be, and that's how far you would go out on each side. So hopefully this kind of makes sense and you like this and you're having fun here. So now, try this last column and actually try and see if you can sketch in what you think the graphs would be based on the observations that we've made so far. Pause the video and do that, and then in 3, 2, 1, here you go. Were you right? Obviously, you can graph it in your calculator as well to see if you were right, but notice that just some more observations that we can make would be that in this one, it's a cosine. So we see that it's on the x-axis, and this is 3, so the petal length is 3. And it's a negative, and that's going to correspond with it being on the left side of the x-axis. For the next one, this is the same as 1 plus 2 sine theta, except that because it's a minus, turns out that the maximum is on the negative side of the y-axis there. Just things to keep in mind. These are what we're going to be learning how to do in 6.5. For the next one, the 2 plus 2, you'd know that the max would be 4 and that the minimum would be 0. So the only thing different about this one than the line above it is that this is cosine, and you'll see that the maximum occurs now on the positive x-axis because this is a plus cosine theta. And then the last one I just threw in there for fun. If r equals 1/3 of theta, then think about it. When theta is 0, r equals 0. And then as theta increases, r also increases, and it actually makes a spiral. And r equals theta is actually an Archimedean spiral is what it's called. But I gave you 1/3 theta so that you can see a little bit more. On your calculator, you may not see all of this. You would only see from 0 to 2 pi unless you went ahead and changed your window. So if you're trying to graph that on your calculator to make sure that you can get a graph to match, you would need to go to your window for this one and set your theta max to however many times you want it to go around the circle. So you can set your theta max to 10 pi, and then that would go around the circle 5 times. So I hope that you have learned some things and that you have synthesized all this information on some sort of note sheet of paper. And have a good day.